Hello, welcome to the second lecture of week number 5 of radio astronomy. So we will continue our discussions with single dish observations. In the last lecture, we have covered some few essentials of radio telescopes, like the reflector antenna design, different types of reflector antenna design, and why a reflector antenna is the most common chosen antenna design for radio telescope, because it's a larger collecting area which produces a sharper beam or less beam with a lesser HPBW or half power beam width, and various others. We discussed also the different reflectors, different feed locations, Cassegrain, offset Cassegrain, prime focus, etc. We also established a very crucial relationship between aperture electric field distribution and far field electric field distribution, which is by a Fourier transform. We also noted that the far field power pattern is a Fourier transform of the autocorrelation function of the near field or the aperture electric field distribution. These are the takeaways from the first lecture, which will carry forward and keep discussing more about the radio telescopes, a single dish, which is the most common radio telescope to be used, and the effect of design and the observing strategies, etc. So the first telescope which we would like to concentrate is one of the largest radio telescope single dish. This is 100 meter in diameter, so from here to here it's about 100 meters, and it's in Green Bank, West Virginia in the United States of America, and this can point to any direction of the sky, given the limitation of the elevation. The mechanical design allows it to only go down to some particular low elevation angles, but apart from that, it can point. It has a elevation encoder over here, so gear, and azimuth over here. It can move this way and point in elevation in this way. It's a kind of a offset Cassegrain offset design, because it's an offset parabolic reflector. So it is kind of it is not Cassegrain, so it is not having a reflector which is coming back to the surface of the dish for the antennas, but it's an interesting thing is that the rays comes like this, hits and then gets reflected and gets to this prime focus point. On the prime focus point, it gets collected, and then there are several feeds which are kept over here, which collects the actual signal and finally sends it down through these rails over here, and then finally down and to the receivers. Okay. So this is more or less the design. So let us see. Yes, so these are the different structures. So number 1 is the primary reflector surface, which is given by this one. Number 2 is the reflector support structure, which is below it. Secondary reflector is number 4, which is over here. Okay. This is 100 meter in aperture, that's all good. Number 5, it reflects to the counterweight, which is over here. Number 6 is active, some controlling the shape of the surface is there. Then the elevation bearing, number 8. So number 8 reflects to the elevation bearing, so that is kind of what points from here. Azimuth tracks is number 12, so which we discussed before already here, and this is from the NRO single dish school lecture notes which we have received. So yeah, that's kind of completes the schematic of this particular dish. Amazing dish, 100 meter in aperture and points to very high precision and accuracy. Let's zoom in to this particular segment. So if you do that, you can see that there is this sub reflector over here. Instead of sending this back to the center of the dish, it sends it to this particular assembly so it can point. So over here all the different feeds are kept. So you can see some of the pictures over here, like those dish. So again the geometry is the rays are coming, hitting the dish, getting up to here, reflected, and then coming down here. So that's the more or less the path which is followed. Okay. So once it comes and hits this sub reflector from the dish, it then sends it down here to be collected over here. Okay, and different frequencies are catered by this particular dish. That will come later when we discuss about science, a later half of this course. But you remember this particular part. This is one of the structures of a radio telescope. It's single dish, 100 meter in diameter, the largest fully steerable dish built so far. The other 300 meter, which is the Arecibo, was fixed on the ground. In the 500 meter also, the FST fast is also fixed on the ground, so they're not fully steerable. The different dishes have different design. This is another kind of design where you have the sub reflector, the assembly of all the elements of the receivers are here. There are counterweights, different types of assembly in the pedestal are seen. Here also there is an azimuth bearing, which is not the like in Greenband telescope. The azimuth bearing was the rail, similar like the VLBA, but in this case the azimuth bearing is a separate thing. The pedestal is fixed. There is separate azimuth bearing over here, and then the elevation is over here. In this particular case, the elevation bearing is here and azimuth bearing is somewhere here. This is a more solid dish, and so this code report structures are different again for different dishes. Here this structure is more or less coming down to the near the center of the dish. Here it mostly comes up to the edge. So different dishes have different structures, and there is no unique design in that case, depending on what kind of science you want to do. Good. So a couple of things to keep in mind when we understand. We said we gone to the reflector design because it has more collecting area. That means it will give to more sensitivity. However, there are forces acting against it. There are several inaccuracies which builds up because of simply the reflector surface. Now, depending on the wavelength you're observing, the accuracy of the surface of the dish is very important. Okay. Like we have seen in GMRT, the design is like a mesh, okay, of wire, whereas in VLA the design is like absolutely fully covered. It is fully solid, and that depends on the highest frequency of observation. If your wavelength goes to so little in size for the highest frequency, then you cannot build this kind of a mesh design. For GMRT, the benefit is that the advantage is that we have the highest frequency in L band or 1.4 gigahertz. Hence, you can live with a mesh design. For VLA, it goes up to 50 gigahertz. So it's very difficult to maintain it. So you have to build a solid surface. Now, even when you build a solid surface, what will be the accuracy of the surface to maintain a perfect parabola? So if there are deviations, then those deviations gets reflected into the error in the signal. So we said that the signals gets reflected by the reflector and gets corrected in the focus. But supposedly it doesn't hit a perfect parabolic reflector, then it will gather some errors. Okay. So here is the easiest way to understand that. So supposedly your best fitted parabola has some error in the surface, which creates an additional path length of epsilon. Okay. For that, the wave have to travel additional distance of twice epsilon, coming and going. And so the error in the phase due to that is given by delta, which is given by 2 pi by lambda times twice epsilon. So now you can see that delta, the phase change, is inversely proportional to the lambda. So as the lambda rises, this phase change becomes negligible. So for lower frequency, it is lower. For higher frequency, it is higher. And epsilon is the deviation. Okay. So, and that causes this relative power gain or power loss for this surface inaccuracy. Okay. Now, so a rough estimate shows that the surface errors must be an order of magnitude smaller than the shortest usable wavelength. So it should be an order of magnitude smaller than the shortest usable wavelength. So supposedly for GMRT the smallest wavelength is 21 centimeter. That basically means that you can assume an inaccuracy of 2 centimeters up to that. Okay. Similarly, supposedly for Green Bank telescope, 100 meter in diameter, the frequency can go up to as high as 100 gigahertz, or lambda minimum as 3 millimeter. If that is the case, then sigma cannot exceed. Another estimate is that the minimum sigma should be lambda minimum over 16. Okay, so roughly. Okay, it's a bit of a back of the envelope calculation. So trust us, that is roughly the estimate you are looking for. So sigma cannot exceed 3 millimeter by 16, so 200 micrometer. That's quite a huge accuracy. 200 micrometer accuracy on the dish is quite large, a requirement. So that's why they have this active control of the shape, which can put into the shape for the Green Bank telescope. But anything else, like there are ALMA telescope operates at very high frequency. Same kind of accuracy is also required for that. Okay. So the next error, which also rises from the single dish measurements, is due to the pointing accuracy or inaccuracy. So for a real telescope, the perfect accurate pointing is not known, because this is such large structures. You see that there is the entire feed is sitting on the center prime focus. So as the antenna rotates, moves in different directions as a function of elevation angle, these things can move a little bit. Only slight movement is required to produce a huge error in the phase. Why phase? Because any movement from the ideal position of that parabolic reflector and the focus will create an additional path length to travel, like same as the case for the surface accuracy. Any additional path length to be traveled by the signal to get recorded in the receiver is corresponding to, gives rise to additional phase, which will create an error. Okay, and so that is the basic concept. Now, so pointing accuracy is inbuilt. Inaccuracy, is inbuilt, because you have a large structures and they keep moving and pointing in different directions, and so little bit of a change in the relative positions of the feed and the reflector is quite possible, not unknown. Okay, even if you keep for a Cassegrain antenna, if you keep all the antennas, all the receiving things at the center of the dish, and below it, still the sub-reflector itself can move. Okay, so in a sense, I mean, yes, I mean, if you want to reduce pointing inaccuracy, then probably Cassegrain has a better chance of doing that than the prime focus, because prime focus you're putting the entire weight of the thing over there, which can create larger pointing errors. So yes, but pointing errors also grows as a function of the half power beam width, because if your beam is quite large, then the pointing error can be, you can live with a little bit higher pointing inaccuracy or errors. But if your half power beam width is narrow, and if you're going to higher and higher frequency, then this lesser pointing inaccuracy also can result in a bigger error, etc. So let's say if you have a tracking error, 1D tracking error in each coordinates like azimuth and elevation, because you have two gears, azimuth and elevation. So suppose you have a tracking error, you have an error because of the motors are not working perfectly, they're not encoded properly, and so they have been moving slowly, or they're a bit behind, they have some errors. So that can give rise to tracking errors. So that resultant tracking error for each direction is given by this, which will result in a RMS error of this rho square averaged. So the on-source gain can be given in terms of this G by G naught. So ultimately, the omega s for the entire tracking error can be summed up as omega s over s equal to z over 1 plus twice c square root of that, where z is given by 4 ln 2 sigma 2 by theta half power beamwidth square. Now let's say we can calculate the largest tracking error in arc second compatible with making flux density measurements with 5% RMS error using GBT 100-meter telescope at a frequency of 33 gigahertz. So for the frequency of 33 gigahertz, first thing to be calculated is the half power beamwidth. That comes out to be 23 arc seconds. With 23 arc seconds, we then go back and calculate this term called Z, and that then gives you the sigma 1 from here, so sigma 2 from here, and sigma 2 then goes to this 0.14 times 23 arc seconds, which is 3.2 arc seconds. Given the relationship between sigma 2 and sigma 1, given by sigma 2 is square root of 2 sigma 1, we can derive the sigma 1 in this case, which is about 2.2 arc seconds in elevation angle. So yeah, that is quite a small error, giving rise to 5% RMS error in flux. Also, it should be noted is that just by thermal expansion of the steel supports for GBT, that can 1 degree Celsius variation can lead to 2 arc second pointing shift in the structures. So overall, I mean, that basically says if you need to have an accurate measurement, you need to have a pointing calibration done. So you need to focus on a known source, see how off that is from the center, because source have a structure, and so does the far field power pattern, and so they have to be deconvolved out and understand that is it pointing at the right place at the right time, or if it is not, then correct for the model from the observation, and then you reduce this error. Because if you are observing at a higher frequency and with a large structure like GBT, pointing calibration is necessary. Same thing prevails for other telescopes, like for very high frequency observations like ALMA, or even with JVLA, it's required. The pointing calibration is very essential. For GMRT also it is done. but not as regularly throughout the observing schedule as for the higher frequency observations, because we are dealing with a little bit larger beam, and so it's the inaccuracies are tolerable. Another important term to note, this is not an error, but this is a contributor to the something called the system temperature, and this is the SCFD, or the system equivalent flux density. So that is given by 2 eta prime K times T-sys over A effective, and that the terms are quite known. A effective is the effective area, collecting area of the instrument, in this case the radio telescope, and S is the flux density to be detected. SCFD, and T-sys is the system temperature, and eta prime is the overall system efficiency, which is the sum over all the inefficiencies built in. So in other words, for a source of flux density S to be detectable, the SCFD must be reduced by square root of bandwidth times the time steps, and so the S by N, S over N, signal to noise ratio, is given by flux density of the source multiplied by the square root of bandwidth times time over SCFD. Okay, this is one thing to be remembered about, that you have to make the SCFD reduce, so that we increase the signal to noise. The noise due to reception of radiation from the ground is smaller. It is possible at shorter wavelength, the secondary focus is preferred. When we have a smaller, higher frequency or smaller wavelength, instead of a prime focus, having a secondary mirror and a Cassegrain, secondary reflector and a Cassegrain kind of a setup is preferred, because the noise due to the reception of radiation from the ground is smaller. In the prime focus case, your antennas are directly looking towards the ground, so there can be spillover, which we mentioned earlier in a diagram, but for Cassegrain setup, it is looking up, so chances of the ground leaking in is less. It is possible to accommodate more receivers for large multi-beam systems. Field of view, that is the region of the sky that can be accurately measured, is larger. That's not always the case, but it is possible to correct for large-scale deformation of primary reflectors by deforming the subreflector appropriately. So there are a little bit of advantages, and so as the frequency goes to higher and higher, the wavelength goes smaller. So these inaccuracies of pointing, the surface, everything gets built up very fast. So you can have a prime focus feed for a lower frequency, like 1.4 gigahertz or even up to 2 to 3 gigahertz. But as you go to higher and higher frequency, 50 gigahertz, 100 gigahertz, having a secondary reflector is a better design than having a prime focus feed. That's what essentially we meant. Single dish radio observations, basic consideration for radio observations made by a single telescope, generally referred as single dish observation. That's the definition. The simplest type of observation you can make is to measure the power of the radiation coming from a source and entering the antenna. As we discussed earlier, that the convolution of the beam, primary beam with the source, is what is the resultant brightness which we observe from the telescope. An equation that relates the power collected by the telescope to the flux density F nu. I must note that we keep changing F nu, S nu, etc., and apologies for that. So here F nu determines the flux density of the source. Okay, so the P is equal to F nu, times A effective times delta nu. So F nu is the flux density of the source, A effective is the area of the telescope, and delta nu is the bandwidth over which detection occurs. Observation strategy is pretty simple. Point the telescope at a source, note the power measured by the source receiver, and use the above equation to calculate the flux density. Okay, so that's how simple this is. But there are lots of details, like the transferring of power to a physical unit of flux density requires also some calibration. Calibrations are done with blank sky, with internal loads, etc., and that gives rise to the real measurement of the power and translating that to the flux density. But in broader perspective, this is a very simple observation. You point the telescope to the sky, to the source. We want to measure the power, the flux density of, and you simply observe it. Now, as you know, the source is not going to be static in the sky, so source keeps on moving. So depending on how long you need to expose to the source depends on how bright the source is and what is your SCFD of the telescope. Supposedly you do not have enough sensitivity, then you have to keep observing for a longer time. That means you may have to keep tracking the source on the sky for a longer time. So for some sources, you may just give a snapshot, just look at the source and you are done. For some sources, you may have to keep tracking for one day. Maybe you have to keep tracking for the next day and the day after, depending on how faint the source is. You need more integration time to resolve, to get the signal to noise ratio higher. Okay, so that's the thing. But nevertheless, the just pointing to the source and tracking the source is all what is required. Now, tracking the source is all what is done by that azimuth and elevation encoders, which we discussed earlier for a single dish telescope. And same for the interferometers. So let's discuss about the basic measurement strategies. So the first one, which comes automatically, is the strategy of switched observations. Let me just select a pen. Yeah. So the process to determine the power emitted by an astronomical source involves subtracting the contribution of the receiver noise. Okay. So say we have these two positions on and off. Now we will come multiple times on this on and off, and there are different meaning of that on and off. Okay, so this time the on and off means in the on position the telescope is looking towards the sky. So the voltage which is recorded by the telescope is some multiplicative terms of the gain, mostly the bandwidth, and the antenna temperature, which is a proxy for the sky temperature, and the system temperature of the antenna of the telescope. That's the on position. The off position is, on the other hand, it is purely looking towards the receiver only and not looking connected to the sky. So why these are done? Because we have a system temperature which is also not very well calibrated. Now, if we want to really understand the antenna temperature from these measurements, we have to remove the system temperature from the equation. So we need two equations because there are two unknowns, TA and TCs. There are many unknowns, but I think we have some handle on the other two unknowns of alpha times G, where alpha is the responsivity of the detector and G is the dimensionless total receiver gain. K is the Boltzmann. So delta nu is the bandwidth which is given. So if you know the V on and V off voltage, you can determine the TA from there. Okay, that's a basic measurement of a single dish observation. Determining of the system temperature. We determine the system temperature by different methods. You can have a noise diode in the system which has a definitive calibrated signal or voltage and measurement, and off when inactive are obtained. So you have a calibrated signal from the noise diode given when in the on position, and off position you have a just the thesis. So if you do that, you can calculate the thesis in terms of this off and cal position also. Okay, this is further derivation of the system temperature itself. So moment you know the system temperature, you can actually deal with only one on position for the calculation and just plug that thesis in here, and you can get the value of the V on, sorry, the TA. Okay, then measurement of antenna temperature. That's the third way. So we have two systems. So we have on and off. So that base essentially gives you the V on and V off. Take the ratio of that to calibrate the gains. You know the system temperature anyway from the T-cal. So you can take care of the T antenna from this V on and V off measurements. That's another way to look at things. So just to summarize again, because it may look confusing. So in the first one, we assume that the gain is very well known. So you just get rid of system temperature by this having two measurements, because there are two unknowns, thesis and TA. Okay. So you can do this on and off measurement when on is to the sky and off is towards the load, and you can do the measurement. Next is you can also have an independent handle on the system temperature by connecting to a calibrator source, internal calibrator source or a noise diode, and then you can measure the thesis from there. If you measure the thesis from there, then you can go back here and put it and also measure the V on and TA separately. Another thing is you can do the ratio of V on and V off. So what happens is it cancels out the gains, and what remains is it just retains the TA, thesis and TA and thesis as a function of on and off. Now, if you already know thesis from the T calibration measurement, then you can put it there and you can get a TA clearly. Okay, that is also a possibility. Very often another thing happens is that you point towards the source, but the source may not be only source which is feeding this entire your beam. So you may have to point on and off to different direction. So on meaning when the source is in your beam, and off position is a standard position where there is no source. Okay, and you keep on nodding between these two positions to get a reference signal only for your source and subtract the background from the source. So various such things will happen, and we will discuss this more when we discuss science done by single dish telescopes later on. Okay. Single dish telescopes, typically you are just collecting the entire power collected by a single telescope, and it's like a single pixel camera, right? So you don't have the image basically shows one pixel or one power value for the entire sky which is inside the beam. Now, but a single pixel also you can use to map the sky. How do you do it? You keep on pointing different position at different time. Supposedly you have this background source a supernova remnant, and you can keep on just pointing at different location in a raster scan mode, and you keep doing this on the fly mapping technique. Basically, this is how the Sardinian radio telescope operates and makes an image, and we have just borrowed it from there. So in a sense, if you do this kind of cross scans in pointing fashion, so for every point you get a value of the amplitude, right? And so you can put them up stack them up in an image form, and you can get the image from the even from a single dish observation. But for images, of course, the interferometers are much better, and we will talk about it later. So uncertainty in the measurement antenna temperature, of course there is uncertainty, lots of uncertainties are there, and like when you first we have shown the radiometer expression in the last week's lecture, where if you take the first round, your variation across the spectrum looks very, very coarse. But if you keep on taking integrate over multiple runs, your this noise reduces. Same exactly what you are seeing over here. The first one is without averaging, second one is with averaging, and you can look at this area, and you can see the noise have reduced. It was so large before, and it has gone down significantly. Okay. However, the signal itself is more strengthened, so signal to noise ratio have improved. Okay. The best place to go back for the antenna temperature errors is going back to the radiometer equation, where you have the error on the TA is linked with the system temperature, and it can be reduced by the more number of times of observations and the bandwidth of observations. Antenna beam is very important, because it again comes down to the thing that your full width half maxima is defining your field of view, and that's your main beam, but field of view defines what is your source. If it is within your field of view, then that cannot be resolved by this particular thing, by single dish. But supposedly a source is extended like that, and you are having your individual pointings as something like pointing are like this. So your single pointing field of view is like this. So then you can get multiple such beams, and you can actually image and resolve this particular source. But supposedly your entire pointing or entire field of view is like this, then you probably will get a single measurement for that and cannot be able to resolve the source. So then field of view basically is a very important topic, quantity for designing an experiment with a single dish. So whether you can image it or not, a particular source depends on the field of view. Okay, beam pattern we have already discussed in details. The beam pattern has for an aperture, beam pattern goes to sinc square function, the primary beam pattern for a uniformly illuminated thing, and this is also what we're discussing over here. Some few things follow. So this is already what we have let me change the color. Yeah, so this is already some expression we have gotten from the previous lecture, where we defined the primary beam, the far field power pattern of the antenna, which has a uniform aperture illumination, and from there you can integrate, and you can get the beam solid angle or antenna solid angle from there, because your P beam is known, so you can define that and get the beam solid angle from there. So if you get that, then the beam solid angle also from the antenna theorem is related to the lambda square over A effective. That is, it depends mostly on the wavelength of observation as well. So if you know the main beam is linked to this expression of the theta, the power collected by the main beam is linked with the measurement of the theta full width half maxima, or HPBW. They are the same. And so the solid angle of the main beam can be gathered from the measurement of the theta FWHM or theta HBPW by using this particular formula. We have already mentioned that we have mentioned and showed that for the aperture, the theta FWHM is proportional to lambda over d, or 1.02 times lambda over d for particular aperture illuminations. Uniform illumination is not necessarily desirable, as we discussed before also, because it can result into large spillover losses. So we mentioned in the previous lecture about uniform illumination pattern, and that's a very simplistic, and it gives you a good handle on all the concepts. But in practically, uniform illumination is not very desirable, because as illumination goes till the edge of the telescope, the dish, so there is chances of spillovers is pretty high. A tapered distribution is more desirable. That's why we showed the second case after the uniform illumination, a tapered illumination pattern. Same here, edge tapered illumination is more desirable, and that's a better case than the uniform illumination. Now let's take up a case study. Consider observing at a wavelength of 21 centimeter with a radio telescope of diameter 2 meter, as in this small telescope in Haystack. The angular resolution of this observation is 1.15 lambda over d. So this is the angular resolution for that. So that comes out to be 6.9 degree. That's the HPBW. So it can differentiate between two sources which are 7 degree apart. So this is almost 14 times the angular diameter of the moon. So if there were two radio sources separated by, say, 8 times the moon's diameter in a simple observation with this telescope at this wavelength, you will not be able to determine that radio emission was coming from two distinct sources. Just a case study. So if you have a 2 meter class telescope, then it will not be able to separate out, even if they're separated by 8 times the diameter of the moon distance. It should be clear that this antenna at this particular wavelength cannot resolve any structure of the moon and even determine its angular size. So yeah, that is the limitation. So certain telescopes are meant to do something and not meant to do others. So that's what all it means. Now let us consider a short radio wavelength, say for example 1 centimeter, and a large telescope of diameter of 100 meter like the Green Bank telescope. The angular resolution for such an observation is about 1.15 times this ratio, which comes out to be 24 arc seconds. So that's the HPBW of this Green Bank telescope at 1 centimeter wavelength. So the same telescope operating at 21 centimeter will be 21 times poorer than this resolution. So in some sense, that what we're hinting is that even at the largest telescope, fully steerable 100 meter class, also having 24 arc second resolution at a 1 centimeter wavelength. So at a lower wavelength, higher wavelength, sorry, at 21 centimeter, it will have 21 times poorer, so almost 400 arc seconds or 440, which is much higher, almost like 6 arc minutes kind of a thing we are seeing. So even though telescope beam becomes pencil beam like, single dish may not be the most desirable telescope type to observe or having the highest resolution, because at some point for certain wavelengths, the higher wavelength part, the size becomes impractical and quite costly to build and to maintain. There is something called main beam efficiency, for example, related to the pointing accuracy. The main beam efficiency is also very important, so that the power collected by the whole telescope versus the power collected by the main beam itself. And if this ratio of the power collected by the main beam or the total power collected by the entire antenna is higher, that means the directivity is higher, that means the sensitivity of the particular telescope is higher towards that particular direction. So if you do the math, if you keep following, because we have been discussing this multiple times, you can see that this sigma main is less than equal to 0.97 lambda square by A effective, is what we get if we have 10 dB H taper illumination. So the efficiency parameter for this main beam can be defined as this, as I said, the sigma of the omega main, which is the solid angle of the main beam, and over the solid angle of the entire antenna. So that is the main beam efficiency. It's also linked with the aperture efficiency. There's another thing called aperture efficiency, and that is linked with the effective area over the geometric area. Okay, so that's the two things. And so if you plug in some numbers for this main beam and the solid angle and the antenna efficiency, aperture efficiency, we get that the ratio of the main beam efficiency and the aperture efficiency is about 1.2. So now we know that the power collected by a single source with a flux density of F nu and a bandwidth of delta nu and effective area of A effective is given by P. In addition to that, we know that the main beam can have its own field of view, so that when we calculate the power collected by the antenna, we convolve the intensity of the source by the beam pattern of the antenna, and it's a convolution, and so actually delta P becomes this. If we integrate over the whole sky, then for different directions, then we finally end up having the power pattern is given by this, where it leads to the integration over the sky. For polarization also, if you consider polarizations, then you have a half factor coming in front. We'll talk about polarization later. When we talk, we will again discuss it further. And so finally, you can use the power and temperature relationship to get the effective antenna temperature in terms of the power. And so P is kT A times delta nu, and so delta nu goes away, and TA becomes A effective over 2K times that integration. Observing resolved versus unresolved sources. So if, as I said, if the half power beam width is is smaller than the distance between the two sources, then you can resolve the two sources or resolve even the single source and see the structure of that particular source if it's an extended one. If the main beam size is larger than the structure of the source, then it will be appear as a unresolved source. So yeah, so I think finally we get the factor of F nu in terms of antenna temperature, and if the antenna temperature is for an entire source, it will integrate over the entire source for a resolved source, and we collect the information of the antenna temperature. From there, once we do that, we can derive the flux density of the source in terms of the antenna temperature by using this formula. The calibration factor is often expressed in units of kelvins per Jansky and is sometimes called degrees per flux unit, or dpfu. So dpfu is nothing but this this proportionality constant, if you can say, between the antenna temperature and the flux density of the source, which is basically the effective area of the antenna over twice Boltzmann constant. For resolved source, the situation is a bit complicated, because that is for the unresolved source, the antenna temperature and the flux density are related by that. For a resolved source, there has to be have to take into account the main beam solid angle as well as the source solid angle. Okay, both has to be taken into account. So finally the I nu, the source, comes out in terms of the antenna temperature and the main beam efficiency, lambda square, etc., given by this. For just to extend for different cases which arises during the practical observations, for a source which fills the sky, uniform source, you have this finally the antenna temperature, which is given by Ta multiplied is equal to the effective area over lambda square times sigma A. So then total solid angle is considered, because that's the of the antenna, and Tb, which is the brightness temperature of the source. So that is the another case. There are several cases where brightness temperature versus antenna temperature, beam dilution. So if a source, for unresolved source, there is an interplay between the source structure and the antenna solid angle, and these two interplays, and that has to be corrected properly from the measurement in order to understand the actual source temperature for that particular part of the source in terms of antenna temperature. Okay, so that's how it get. So the Ta, this decrease in Ta relative to Tb is referred to as the beam dilution, because the source solid angle over the antenna solid angle, if the source solid angle is lower than the antenna solid angle, then the brightness temperature of the source may appear to be larger than actually the measured antenna temperature. Okay. In addition, for spectral line observation, so if you're not observing, not looking only for the amplitude or the flux density of the source, but also looking for spectral response. So suppose you have a atomic transition line, like for the hydrogen hyperfine transition from 1s to 2s at 1.4 gigahertz. That's a specific line at a given frequency. So you want to observe those lines, spectral line observations. Then the spectrometer has to be configured, and you have the bandwidth of observation is important. The central frequency has to be tuned, because you want to keep the location of the spectral line, or which you propose to target, has to be in the center of the band, and spectral resolution has to be such that you resolve the entire spectral line into several such channels. We will come to this later on also when we discuss about spectral line observations, both with interferometry as well as single dish. So, but it needs to be discussed here for completeness, because yes, if you are looking at a spectral line, then the number of spectral channel has to be sufficient to reconstruct the spectral line. The center of the spectral line of the band should be configured such that the expected spectral line should show up at the center of the band, because sometimes there are other most of the time other things has to be done, like continuum subtraction, etc., which requires you to have sufficient channels on either side of the band, on both sides of the spectral line, to be subtracted to get the line with more significance. These are just a few more recipe for getting a good spectral line observations. Obtaining radio images, of course you have a single pixel camera with a single telescope, and you can do the raster scan as we discussed. There are other methods to increase this area of the coverage and having multiple pixels. So if you can think of something like having instead of a single feed, you have an array of feeds at the focus. It's also called a focal plane array. We will be discussing it in weeks to follow more. But that's like if you have a 3x3 focal plane array, that means you have a 9 pixel camera kind of at the focus, and so that gives you more field of view and more resolution within that field of view. There are single dish observations have a relatively small number of antenna temperature measurements, often just one measurement per pointing direction. Then imaging using single receiver telescope involves pointing observations, moving and repeating, move the telescope to a new position, and then again repeat the observation process, covering the desired sky area. Converting antenna temperature, so convert measured antenna temperatures at all positions into a comprehensive radio source map. These are all already discussed. And there are imaging challenges. Of course, you can do raster scan and make an image, but that image won't be as good as the image which you will get from a radio interferometer, and the reasons are obvious. But we will definitely cover both the aspects of imaging when we discuss the interferometers and the advantages and disadvantages of each techniques. So you have antenna temperature, which is kind of again is a measure of the source intensity convolved with the beam pattern, far field beam pattern, and that's the final measurement of the antenna temperature. Given the different size of the primary beam pattern, given different size of the sources, you can have different effects of the convolution between the source structure and the beam. In this particular case, we haven't determined the size of the source itself, but given the thing and different beam, the result can be different for different telescopes. Yes, just elaboration of that. So we can keep on doing it in detail for different shape of the beam, for different shape of the source itself. You can do that. And finally, you have to deconvolve the beam from the measurement to be able to understand the source temperature and source structure clearly. To calibrate the telescope, we have already pointed out in the beginning of this lecture that a lot of issues happen because of pointing. So pointing correction has to be done. You need to have to choose a particular pointing source to observe that and correct from it. Details are given over here. Calibration of the gain is necessary to get the gain out from the measurement of the antenna temperature. Effective area also has to be measured, and the gain curve as a function of frequency, elevation, or different antennas have different, telescopes have different responses, or the gains as a function of elevation, frequency, temperature, ambient temperature, it changes. So you need to understand the gain as a function of all these different parameters before you can correct from the ongoing observations. Again, measurement of the beam pattern and the main beam efficiency is also very vital, and those has to be known a priori to be able to get a sensitive observations. And also this radiometer equation at the end, we have revisited it multiple times. So you need to know the system temperature quite well. You can calibrate it as we have shown earlier, and you can derive this this RMS noise or sensitivity measure for the given telescope. If you know the sensitivity of the telescope, you can derive the minimum flux density which can be measured by your telescope in terms of the SCFD, and that's also we have discussed earlier, and so this is just for the completeness. There are different types of polarization also of the astronomical sources, and different telescope beams have their own polarization characteristics, so they have to be calibrated out. Different hardwares, different feeds have different effects, so all those can be done. And so we come to the end of another lecture, and this is the last lecture of this particular week. We discussed in depth how a single disk observation works. We tried to cover the essentials of how the calibration is done between so that we can get an accurate measurement of the source properties like the flux density, the measurement of the source size, the structures, and how to deconvolve out the primary beam characteristics of the antenna telescope itself to get the accurate measurement of the source in the sky. However, I think things will become more clear when we take an observation into account and explain this more. So that will come to the next half of the after the interferometry is done. We will talk about the science with the telescopes. There we will take a particular use case and discuss that to make these concepts more clear. So some of them are a little bit repetitive. Some of these concepts are here for completeness. So if you are feeling overwhelmed by all of this information, don't worry. We will come back and use it and show it how it is used for actual observations in later part of this in this course. Again, this is the reference list. We do prepare our notes and the slides based on existing literature, and we try to reference them when they are used on that particular slide. But if we have missed, I apologize for that. This is a disclaimer for that. And so I hope you like the lecture, and thanks for joining. See you in the next lecture next week. Thank you. Bye.